Yes.
How do I upload that? Do I just download the stuff from ID IntelliJ and upload it to Moodle?
Just upload the .java files.
Okay, so just because I have to make copies because when I'm transferring from the clips to IntelliJ, they didn't correct code match. Plus, I'm working with Java 12 instead of 8, which is on most computers.
Well, 12 is on the upgrade path. It's upward compatible. If you write something for Java 8, it's going to run in Java 12.
Okay.
Yeah, it's not a problem.
But if I write something in Java in 12, it can't work with 8. And that's what the program was written in.
That's okay. The program's written in Java 8, so the Java 12 JVM will happily run it. No problem.
Okay. Just pull the files off their locations in the file.
And then upload them to Moodle.
Okay, I was just making sure because I had to make copies.
Very good. Very good. All right. Good morning. I'm going to try an experiment. I got this relatively new laptop that lets you draw on it. I'm going to experiment with drawing up here using the laptop rather than the chalkboard. We'll see how it goes. I want to go ahead and review key concepts we've talked about over the last few class periods. So some key ideas include the heap versus the stack for memory allocation. We have talked about classes quite a lot in Java. And we've talked a lot about arrays and how arrays work, how efficient they are. So we've discussed the efficiency of arrays. And we discussed that in terms of several operations. Or, oops, not add, but rather overwrite / read an element. And then we discussed insert an element. And in that context, we explored the fact that inserting is relatively expensive. So this was cheap. And then this cost a lot of time. It was expensive in that sense. And wait just a second. I'm still kind of figuring this thing out. There we go. Cool. So we're going to take some of those themes and think about them in some different ways today in considering an alternative to the idea of an array. Now, something that was pretty interesting, I think, that we talked about last time was what it meant to resize an array. Of course, you don't really resize the array. Instead, you take advantage of the fact that it's allocated using the heap. So when I've got a variable, which is something like int bracket a equals new int 5, what's really happening is that within the memory of the computer, a is pointing to a reserved block of memory that contains 5 elements. This means later on, I can do something like this. I can say int bracket b equals new int 10. And having done that, we have b over here and it's got 10 elements. And now the really crucial part is I can say A equals B. And what that does is it means A is no longer pointing at that original block. Instead, A is now pointing at the same block as B. Something worth thinking about here is when we talk about A and B pointing at things, what are they? Part of the answer, which can be a little confusing, but I'm just going to ask you to bear with me on this, is that all A and B really are integers. And this may sound like a weird idea, but what they are integers that correspond to the memory locations that have been reserved for those arrays. So when I talk about A pointing at an array, what that really means is that A is an integer with a value like, say, 8,000. And that array starts at 8,000, and then, whoops, didn't mean to do that. Said, still getting used to the software here. Let's make that big again. So that array is at 8,000. And then, of course, that's where the first element is. The second element is going to be at 8,001. And then we'll have an element at 8,002 and 8,003 and so forth. So this idea of a pointer, or in Java terms, what is called a memory reference, is crucial whenever we're thinking about the heap. The heap contains data accessed through memory references. As a side note, we hinted at this before, but I want to talk about it again. Once A is no longer a reference to this block, the question arises, well, was anybody else referencing that block? And if the answer is no, which in this case it is, this block is now what is called garbage. Where garbage is the technical term for memory that has no live references. Nothing is pointing at it. And so what do we do with garbage? As programmers, you do nothing about garbage. Now, the Java virtual machine periodically cleans up garbage, doing what's called garbage collection. How precisely that works is beyond the scope of where we're at today. I think I'm going to discuss it with you all much later in the semester once you've got a little bit more of a background on this sort of thing. But the idea of garbage collection is it figures out which heap blocks have live references. We're going to keep those, and everyone that doesn't have a live reference goes away. This garbage collection process is largely transparent, with the occasional little problem of what's called a collection pause. That is, sometimes if there's a very large amount of garbage, it might actually slow the program down a little bit while it collects it. For most of what you'll be working on, this should be a non-issue, however. The thing is, this whole idea of a memory reference lets us think in different ways about what kinds of data structures we can build. That is, an array is this big flat section of memory, and we have one reference that tells us something about it. All other data structures we're going to look at are going to be built on top of either the raw idea of an array or other means of using memory references pointing at objects in the heap. So it winds up being very important to get comfortable with the idea of a memory reference because it's just going to keep coming up over and over again in lots of different contexts that we're going to be examining in this class. So we're going to take this idea of a memory reference and think about a different way to implement a sequence of items. Because that's one way you can think of an array as representing a sequence. So what do I mean by a sequence? Well, it's just a list of data in order. Now that order doesn't have to have any relationship to the data itself. It's just that there's a notion of this thing comes before this thing comes before this thing. In particular, I wouldn't want you to get the idea that the fact that there's a sequence means that it's sorted. We will be talking about sorting in painstaking detail this semester. By the end of the semester, you will all be sorting experts. But the idea of having a sorted sequence presupposes the idea of having a sequence at all. Okay. So we're first going to think about sequences, and ultimately we'll talk about sorting them and organizing them. We'll also talk about why you would sort them. There is a fun little historical anecdote, which I'll no doubt repeat when we get to the sorting section. But an early motivation for the creation of sorting algorithms, and by early I mean like the 1960s, was to try to write software to translate text between languages. That technology has gotten hugely better in modern times than it was then. But people would have basically take dictionaries and sort them so that you could quickly find the appropriate words to translate. One such system early on translated the famous quote from Jesus in the Garden of Gethsemane, the spirit is willing, but the flesh is weak, into Russian and back. And when it came back from Russian, it had become, the meat is rotten, but the wine is good. Yeah, you have to think about it for a second, right? Yeah. So, even Google Translate has its occasional howlers along those lines, especially with non-European languages in particular. A couple years ago, for a senior thesis, one of our Rwandan students wanted to put together an English to Kenya Rwanda translator. And let's just say we ran into more than one problem along those lines. So that's a sequence, a list of data in order. An array can implement a sequence. How so? If we use an array, the sequence is implied by the index order, right? So whatever is at element 0 is in some sense before element 1. Whatever is at element 1 is before element 2. And what's at 2 is before 3, and so forth. So that's an ordering based on their position in the sequence. But this isn't the only way to create a sequence. So here's another. Here's how you can think about this. Let's imagine that you've got a data structure consisting of two things. So I'm going to just pretend we have a class, and I'm going to call this a node. And in this class, we have some int, which represents a value of the node. And then we have, let's see, there we go.
You may have to go back up forward. Can you just send me a copy of this later?
Yeah, absolutely. Yeah, I'm recording this as we speak.
Okay, because
So,
I missed a lot of it, so I'll just get a copy from you.
Yeah. So looking at this data structure, it provides an interesting opportunity. You may be a little puzzled by it, actually, in the sense of I created a data type, and one of its elements is a value of the same data type. Just to bring in some vocabulary from last semester, which you saw briefly, but which you're going to see over and over again in painstaking detail in this class. This is an example of data recursion. Everybody remember the term recursion? What was recursion back in Computer Science 150? Somebody tell me? What was recursion? Yeah, Paxton.
Function called itself.
When a function calls itself. And It was a pretty powerful idea, right? What did we use it for, Paxton?
What I can remember, we had a lab all about it where we were using recursion with fractals, which I can't remember what those actually are, but I remember that we used them.
Used it with fractals, yeah, Caleb?
If you want the function to go through, like, say, like a list or a dictionary and check every single entry for something,
Mhm.
you can use recursion.
Right, you can replace looping with it. Yeah. The idea of fractals was that they have a top level structure which gets replicated at lower layers. And that's where recursion came in, is you do the same kind of thing lower down when you're drawing it as you did further up. Let's see. Did anybody take the class last semester? Last semester as opposed to last fall? Yeah, what did we do recursion for?
In the spring?
Yeah.
When me and Caleb in that class together, we did the lab that he was talking about
The
too.
fractals?
Yeah.
Did anybody do the lab with the file system?
With searching through the files.
That was the searching Enron.
Yeah.
That too was recursion. And in fact, you can think of the file system in the computer as also being a recursive data structure. Here's what I mean. Let's say I bring up File Explorer. When I bring up File Explorer, let's say I go to Documents, okay? So Documents is a file folder that contains a number of documents, and then it contains more file folders. And if I were to select a file folder, like assessment. No, I didn't mean to, yeah, there we go. I go in, now there's more stuff. And if there were folders in that, I could keep going, right? So that's an example of a recursive data structure. A data structure that has reference to elements of its own type. And the same thing goes with this idea of a node. It's a recursive data structure. So we tend to draw these abstractly in the following manner. We'll draw a node as a circle, and then we'll put a value in it. And then we'll put an arrow, and that arrow will terminate in another one of these guys. And then we might have another arrow that terminates in another one of these guys. Any thoughts as to how this sequence could ever possibly end? What would it take? Can this go on forever?
Abstractly.
Abstractly it can. Can it go on forever within the memory of a computer? No, that would require infinite memory. I mean, Tate is right. Abstractly speaking, yeah, it can absolutely go on forever. But within a finite memory, no, it can't. So how might this resolve? How might this end? Thoughts?
When you have the two in.
Right, but I meant structurally, how might it end? So what could this point to such that it stops pointing? Where does the buck stop? Or must it stop, even with finite memory? Well, here's one idea. In principle, right, it could just loop back around to something earlier. That has its place. It's not what we're going to do quite yet. It can actually stop with a special value. That special value is called null. Any variable in Java, which is a memory reference variable, can have the value null. And if you just declare the variable without initializing it with a value, its value is null. What null means is that there's nothing there. So null is the value of a memory reference that does not correspond to any reserved memory in the heap. That's what null means. Now, let's imagine you create a class and some objects of that class, and you also have a reference for an object, for a variable of that type, which is null, and then you try to call a method on it. Any guesses as to what happens if you try to call a method on a null reference? Some of you may have experienced this already. Has anyone yet seen the obnoxious error message, null pointer exception? Yeah, a few of you have. You get a null pointer exception if you invoke any method on a null reference. Let's write that down. If you invoke a method on a null reference, you get null pointer exception. And this will halt your program. It will stop it dead in its tracks. Why must a program stop dead in its tracks if you try to make a method invocation on a null reference? Why must that happen? Bless you. Any thoughts or alternatives? You're welcome to suggest an alternative to the program halting. Let me phrase it differently. Is there any sense in which it makes sense for a method to execute on a null reference? Why not?
Nothing to do. Like you can't do anything with it.
You can't do anything with it because there is no it. All regular methods assume that there's an object with concrete data on which they can operate, right? So think about your tit-for-tat objects. A requirement of the assignment is that they all maintain some state, right? All of them have to do some record keeping. So every time opponent move gets called within your tit-for-tat playing, or your prisoner's dilemma object, not necessarily tit-for-tat, but in your prisoner's dilemma object, it's changing something every time you call that method. Now, if you have a null reference, there's nothing to change because it's pointing nowhere. And so when we try to do that, Java responds by saying, sorry, I can't do that. So you must stop now. Farewell. This is a good thing because at any point where you would try to call a method on a null reference, that's a bug, right? That is never the behavior of a correct program. That is always an error. So it's just a way of the Java virtual machine saying, I'm not going to let this program continue in the presence of this mistake. Okay. So that's what happens. So typically, one of these sequences is terminated with a null reference. Now, if we're going to avoid invoking a method on it, then we're going to want to make sure that it's there, you know. So any questions so far before we start coding one of these up? These things have a name, by the way. This is what is called a linked list. This is called a linked list. The term list emphasizes a sequence in order. Linked talks about the various memory references that hold it together. The various memory references that hold it together in place. So actually, before we code it up, we're going to talk about a couple of conceptual advantages of a linked list. Let's say that you maintain references to both the start and the end of your linked list. So you've got some variable here, which is end, and some variable here, which is start. Okay? And of course, what type are these variables going to be, do you all think? Actually, they're just going to be node typed, right? I mentioned, all of these reference variables deep down are integers, but they're not ints in the type system. Their type is always associated with the type of thing they point to. So deep down, of course, they'll be integers, but their type in the language is going to be node, okay? So start and end are nodes. So now let's imagine I want to add to the start of the list. Well, what I'm going to do is I'm going to take my value and then I'm going to tell it to point at whatever start is pointing at, and then I'm going to tell start to point to it. Here's a question for you all. Does the amount of work I have to do to bring this about depend on the size of the list? Not at all. So I have a cheap add to start for my linked list. Now let's think about the end. Let's say I want to add something to the end. What I can do is I can tell the ends next to point at my new node, and then I can tell my new node to point at null. And then I make my end my new node. Does the amount of work this required depend on the size of the list? So this is interesting because the linked list kind of gives me a victory over the array already, right? Because I can inexpensively add to either end of the linked list. We talked on Friday about how with an array, that's not possible. It can't be done, right? But with a linked list, you can do it, which is pretty cool. For that matter, let's say I happen to have some kind of inside reference handy. I can very easily insert a node after it, right? I can say new node, point to its successor, and then old node, point to that. Does that depend on the number of elements in the list? Of course, finding this might require that. It's a subtlety. But once I have that, altering its size doesn't depend, or adding something in the middle doesn't depend on the size of the list. That too is efficient. So this is great. So linked lists solve all our problems with arrays, right? Are there any imaginable downsides to the linked list? It does take more storage. That's true. And the reason Elijah is correct to point out that it requires more storage is that in an array, each element only needs enough memory to store the element value itself. With a linked list, you need an additional memory reference for every single element. So it's going to take, with simple data like an int, basically twice as much memory. With really large data, let's say the elements of your list are themselves large data structures, then the overhead becomes minimal. But with something like an int, yeah, it takes twice as much memory. Good, that's a disadvantage of a linked list. Are there other imaginable disadvantages of a linked list? Changing the node value. So let's say I already have a reference to the node I want to change. That's very easy. Let's say I want to change the 10th element. If I want to change the 10th element, I need to start at the start and go 1, 2, 3, 4. Well, I have to go for more list than I actually have, right? I have to hop down through my list 10 times. So let's kind of summarize some of the trade-offs. Linked list versus an array. So it is really good for add to, I didn't quite mean to do it like that. Here, let's try that. Yeah. Add to the start or end or the middle. That is a plus for a linked list. For an array, add to the end was good, but a minus was add to the middle. Oops. No, I don't want to type here. Go away. Or the start, right? Now, a big plus for the array was random access. You can immediately jump to the 10th thing, the 100th thing, the 1000th thing. And that is a big minus for the linked list. And a plus for the array is it has a small memory footprint. And that is a minus for the linked list. Sorry. Memory footprint. Yeah. So there's some subtlety there in that with an array, if you're resizing it, you might have to reserve unused space for every element. And so in that sense, it's twice as big, except that a lot of that eventually gets used in practice. And so more often than not, arrays are going to have a memory footprint advantage. So linked list arrays. So these two data structures, the linked list and the array, are primary means of implementing sequences. You will see these implemented in just about any programming language in different ways. For various reasons, some language environments prefer lists versus arrays or vice versa. For instance, if you ever take one of Dr. Yorgi's courses where he teaches Haskell, the Haskell language tends to prefer linked lists for reasons that make sense within that language. A language like Java tends to prefer arrays. But both of them are usable, actionable sequence representations. Sequences wind up being extremely important data structures in practice. So we definitely need to get accustomed to working with them. Any questions so far? All right, so let's spend a bit of time exploring what an implementation looks like concretely. So to that end, I am going to transition over to IntelliJ, and let's try putting together a new project. And so let's call it list one. And we'll put it in a new window. And now we're going to need some code. I forgot to make it a Java project. That is so silly. No, it's a Java project. So why won't it let me create class files? Okay. Get over here. Ah, here we go. Okay. So I'm going to create a Java class. I'm going to call this class node, kind of like I was working on in the scribbled part. So I've got public class node, and I'm going to say private int value and private node next. So in terms of the internal data representation, that's all we really need for a linked list node. Now we're going to think a bit about the methods it needs. And here I want to bring up something that I should have talked about earlier. It came up in office hours last week. If you don't give a class a constructor, Java will simply make one up for you. That's just what it does. So if I don't give Node a constructor, it will be more than happy to generate a constructor for me that will give a value of 0, and next a value of null. So for every built-in data type in Java, there is what's called a default value. So for integers, it's 0. For floats and doubles, it's 0.0. For booleans, it's false. And for all memory reference types, it's null. So in principle, I don't have to create a constructor. I'm going to go back and create one in a couple minutes, but for now, we're going to live without one and just see how far we get, right? So I'm going to create some methods. Because there's a very strong convention in Java to keep data private and methods public, it's common to write methods called getters. And so a getter, like get value, is a method that returns the value of a data item. You don't always need getters for your private data. They are useful sometimes. In this case, it's definitely useful. But you don't always need them. Sometimes you'll be able to define a data abstraction that avoids having to make reference to that. And then I'm going to create a getter for next, like so. And now I'm going to just throw together a main so we can try it out. So node n equals new node. So we're just going to try this out and see what it does. So it's going to build it. It's going to take its time building it. Here I am twiddling my thumbs. Okay, it's doing something else while building it. Oh, that's great. Okay, so it ran. And so when I printed the value, it printed 0. And when I printed n.next, it printed null. So something about this that I find tremendously irritating is that when I create a new data type, I don't really want, in order to examine or inspect it, feel like I'm required to individually print out the data items in it. That just seems very silly to me. And in fact, Java provides a way to think about this. So let me first show you the following. What happens if I print n all by itself. Check this out. If I print n all by itself, first I printed the value, then I printed next, and then it printed this complete gibberish here. So let me talk about this gibberish. The gibberish begins with a noteworthy piece of non-gibberish, namely the data type, node. Then there is an @ sign. And then what follows really is genuine gibberish, right? 6A-CB-CFC0. Clearly, that is incomprehensible nonsense. What it actually is, although, again, it really is kind of nonsense, is the memory location where this node object was positioned in the heap, expressed using base 16 or hexadecimal. Why base 16? Base 16 is popular when thinking about things like memory addresses because every base 16 digit is the equivalent of 4 binary digits. So you can think of base 16 as a really compact way to express a really long binary number. So that's why base 16. Nevertheless, in practice, this is useless. Like, so utterly, completely useless as to beggar the imagination. So what do you do about it? This is the default implementation of a method every class in Java has, which is called toString. And if you don't like what it does, you can make up your own, which is what we are now going to do. I am going to override public string toString. I'm going to make up my own toString method. Why? Because I just ran out of patience with hexadecimal. So here's what it might look like. I might say something like, if next is null. So here's an example of making sure I don't call a method on a null reference. So if next is null, I'm just going to return integer.toString of my value. Otherwise, I'm going to return my value plus a semicolon plus next dot toString. Now, to really make this interesting, I need to have a more concrete list. To that end, I'm going to come up here and I'm going to define a constructor that lets me put together a nicer list. So this constructor is going to take 2 parameters, a value to where? Yep, sir. Let me adjust this so it remains visible with what I'm about to do. Yeah, there we go. Let me scoot that down again. So in my implementation of this constructor, what I'm going to do is I'm going to say value equals v and next equals n. But now notice I have a compile error here. By defining my own constructor, the automatically generated constructor is no longer automatically generated. But that's okay because I really want to do something more interesting. So I'm going to say this node is the value 5 and its next is null. And now is where things get really interesting. I'm going to create another node, which I'm going to call N2. I'm going to make it a new node with the value 8, and its next is going to be N. In other words, N2 is going to be the start of a linked list, which ends with N. But why stop there? And now here's the fun part, is I'm going to call println on N3. Doing that is going to invoke the toString method. Let's watch what happens. It's building, it's parsing. It ran. So here's what it printed. It printed 10, semicolon 8, semicolon 5. Let's go back and look at toString and get a feel for how it worked. So when I called toString on N3, what happened was it came in here, and tell me, what happened at the if statement when it was N3? Was N3's next equal to null? No, correct, it was not. So it went to the else, and it returned the value for N3, which is 10, plus a semicolon, plus it then called toString on next. Now, it can't complete this string concatenation until this recursive call completes, right? It needs to have values in place for everything being concatenated before it can return. So it actually pauses for a moment, sits there, waits patiently, and asks N2 to stringify itself. So we come in with N2, is next null? Correct, it's not null. So it comes down here, it puts an 8 and a semicolon together and calls next.toString. And now it's going to be on N. So it comes up to N. Now is next null? Yes, that's correct. Next is null, so it takes the value 5, turns it into a string, and returns it. Now the recursive calls begin to unwind. So N2 was waiting desperately on what N's string value was. It finds out that it's a 5, so it can concatenate 8 semicolon 5 and then returns to the waiting call for N3, which then sticks a 10 and a semicolon in front of it, returns it, and then println is finally able to complete. So this is a very important idea to think about in terms of data structures, is the fact that a recursive definition lends itself to a recursive implementation of methods. So if I've got this sequence, which is defined recursively, it becomes natural to write a method that traverses it recursively. I'm just using the recursive structure that is already in place to define my traversal. As a side note, in practice, for any hope of debugging, every class you create, you're ultimately going to want to have a toString method so that you can look at it and it doesn't look like node at blah, 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 blah. And so that can be pretty handy. Well, we've only got 2 minutes left, but we'll talk about it. So a last thought, and maybe we'll spend more time on this on Wednesday, is, there we go. Hit Alt-Enter, and then I can come down and create a test for it. So I'll create a test. I don't want a groovy J, I want JUnit 5. It's not in the module, so add it. We kind of saw this last time when we were looking at writing a unit test. And okay, and then hit Alt-Enter, add that library to the class path, bam. Okay, So now I can start writing some tests, right? Test, public void, test one. I'm not feeling creative yet, but as you know, we can always rename things, okay? So in test one, I'll say node n equals new node, 5 null, and then assert equals 5 n dot get value, like so. And then I might say node n2 equals new node 8n. And then I might do something like this. Assert equals 8 semicolon 5 comma n2 dot to string. So now, oh, whoops, I just ran node. I really want to run my unit test. I want to run node test, and I get my nice green check mark. It passed the test. Note the value of defining this unit test to automatically check the result, as opposed to, say, having a main, which you can run anytime you want, but then you kind of have to manually see, is it doing the thing I wanted to do, for instance. And so this is a really nice test because it tests my ability to traverse the list, even in a relatively small form. So I've been experimenting with this a little bit. I am hoping that today's lecture will be available on YouTube later this morning, and I'll post a link to it in the Moodle page for the class. I will look forward to seeing all of you in lab tomorrow, and we're going to, in this week's lab, experiment with both resizable arrays and linked lists. See you then.